This is my Physics 2212 Lab 2 report on magnetic field of a bar magnet. Um, Before we get started, I would like to go over a table of contents. We'll go over some introductions, and then go over the results of the lab, and then the coding portion of the lab. We'll answer some what-if questions, and then we'll end with a conclusion. So, the introduction. So, important concepts and formulas. Um, One of the really important concepts is the Biot-Savart law, which generally finds the formula for a magnetic field of a dipole. Since a bar magnet acts as a magnetic dipole, we expect this magnetic field to fall off proportionately to the inverse cube of the distance, which you'll get if you use that formula. And then we'll also find V bar, K is equal times R to the n power, and through this lab we'll find what n is, and we should expect it to be about -3. We also have the principle of superposition. Since our magnet isn't the only magnetic field in the green, since Earth creates a magnetic field as well, the magnetometer that we will use for this lab will measure the net magnetic field, so we need to adjust our magnets to isolate Earth's magnetic field away from the magnet's magnetic field. So what is this lab? In this lab, you will measure the distance dependence of the magnetic field due to a small bar magnet, and then compare your measurements to distance dependence predicted by the equations for on and off axis magnetic fields derived from the Biot-Savart law. So, some results. Before we go into results though, I want to talk about how I set up this experiment. So I set up my phone and rotated it until the exponent read 0 on the magnetometer app. I aligned my phone with Earth's magnetic north and south axis so that when we actually did the experiment, we would compensate for Earth's magnetic pole. And then we figure out the east and west axis of the magnetic field. And it's only magnetic field's affected by the x component of the sensor, effectively separating it from Earth's field. And then we slid the phone up and recorded different magnetic field distance targets from 20 microteslas up to 220 microteslas. Right. So here is some of the results. To find the distance dependence denoted as n, I plotted the natural log of the magnetic field against the natural log of the distance. And this slope gave me an experimental distance dependence of minus 2.9987, which is about 3, which was expected. And then this also gave us, using the y-intercept of a magnetic dipole of about 1.7996. And then you can see the Tesla meter app on the left-hand side as well. So, when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Now, onto some coding. Up there is a formula for the dipole, and then some formulas for setting up the vectors to show the magnetic field. I wanted to make sure that, in theory, the physics matched up with what I found experimentally. So you can see here, this is what it would look like, and I believe this is an accurate depiction of what was going on. So some what-if questions. In the experiment, you oriented your setups as to compensate for the magnetic north. If you hadn't done that, and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field, how would your results have changed? Since Earth's magnetic field superimposed and magnetic field superimposed in general, the vector sum of my magnet would have been adding Earth's magnetic field as well, which would offset my data and I could never approach 0, which would cause my n value to be inaccurate or impossible to calculate with the magnetic dipole moment. And the plot would be like a curved line instead. And imagine you had two identical magnets. What if you redid the experiment, but instead of a single magnet, used two identical magnets stuck together end to end? How would you expect your experiments to differ? So if I had two magnets instead, basically the magnetic dipole moment would be roughly double of that of a single magnet, since it makes it larger dipole of two magnets. And the magnetic field at any given distance would be stronger, but the shape wouldn't change. So n would still be approximately -3, but you would see a shifted graph. And to conclude, Some things that might have gone wrong with this experiment would have been if there's like other magnetic items or like metals or electronics nearby when I was doing the experiment, or if things like unshifted or if my data was put in wrong. Thank you.